Thank you very much for being here. My name is Vladimir Vishnevskii. I would like to offer the talk that is called Test-Driven Development of Embedded and System-Level Software. This is this is a further elaboration of the testability topic that I touched last year here on ACCU with the talk C++ in the World of Embedded Systems, where I highlighted some of C++ features that can facilitate testability of embedded code, and also would like to further emphasize the importance of test-driven development and encourage the engineers who are working with embedded code to use it, adopt it if it's not yet adopted. So we will talk a bit about the scope of the talk, so what we mean by embedded system-level code. Then we will review a bit test-driven development process, and then we focus on unit testing as the essential part of test-driven development. So when we are talking about embedded development, what it is and how does it look like? So we have software that is developed on a host platform and deployed on the target platform. This is cross-platform development. We also have some limited diagnostics and debugging possibilities. Yeah? So we can have either specific limitations that can be introduced on purpose to limit the access to the system. We can have the system that is physically hardly accessible. We can also just have complex technical solutions to have some debugging capabilities. And also, what is of course often the case, the software can be just dependent on the hardware or on platform API. So some applications, they can be resource constrained, so there will be no abundance of operational memory storage for executable and computational power. And some types of software, they should be designed for runtime efficiency. There can be some real-time components, there are also device drivers, and quite related to this, or not exactly the same, but we also have some types of the software that not necessarily deployed on the different architecture, but something that also requires some specific environment to be executed. For example, we can have some software that is located between operating system and application, providing some platform to the application that can be dependent on the system APIs, also requires some specific configuration like networking, and can perform some actions that are not supposed to be executed on host, and where also runtime efficiency can be applied. So this is some form of the system level code. And if we summarize this, we will see some similarities that are typical for these types of applications, but not exclusive. Yeah? So we have some dependency on IS APIs. We have some also runtime efficiency requirement, but those are not exclusive. Yes, runtime efficiency is also overlaps a lot with the low latency applications. So there's a quite similar problematic there. And now a bit about the test-driven development process. Yeah? So I will just read the definition that I took from Wikipedia, the open source one. So test-driven development is a software development process relying on software requirements being converted to test cases before software is fully developed, and tracking all software development by repeatedly testing the software against all test cases. So it is not specified what kind of testing is used here, but as we need to repeatedly retest the application against all test cases, most likely implies that there is some automated testing strategy involved. Yeah? That means that, so that would imply that the testing software is supposed to be implemented before and parallel with implementation of the production software. The process will then be ubiquitous, because then testing should be considered during planning, architectural work, and implementation. And as consequences for this, it would be good if the software will not be introduced into repository without sufficient test coverage. So if we look at types of tests, there are different classification of tests, but if we look at the object under test granularity, then we will have three types. Yeah? So some end-to-end tests that test the whole system. We also have integration tests, some subsystems that are, when they are tested, and unit tests that test the units, so their classes and functions independently, so without dependencies. If we look at typical test-driven development cycles, so we can see that this is an iterative process. So the implementation is happening iteratively with testing, and some parts of the testing are happening on host, And some are required to be executed on target. Some parts of integration test plus end-to-end test. For cross-platform development, including embedded, we also have some intermediate state, so where we need to have something executed on emulation if it is available. Otherwise, it shifts on target. And we also can see that this arrow, it shows increase in complexity of the test implementation and of the test results, plus it shows increase in the runtime of the test, so how long does it take to execute one, so and how often do we execute the tests. So the execution period increases, so the frequency kind of reduced. So unit testing is the most frequently executed, the simplest one, so that where we test the simple units. End-to-end testing, opposite to this, is the most complex one that produces the most complex results. So for end-to-end can also be used to drive some development of the features. For example, as a part of the practice of acceptance test-driven development, but this is a bit of the scope, out of the scope. For embedded systems, integration testing and end-to-end testing, they can be really complex solutions. Why? Because they can be complex software, hardware solutions, because their integration testing requires software, hardware test doubles to substitute some parts of the missing parts of the system. The end-to-end testing also requires the interaction with the system quite often. So that it can be typically having non-standard interfaces. It should definitely be considered during the planning, because it's also a large work item. But if we look at some complex embedded solution, hypothetical one, of course. So where we have multiple blocks that are connected with each other, of course, there is interaction with the primary system where we are embedded in potential communication with the backend. So most likely there is some strategy, automated strategy for verification of the solution is required. So because we need to have some integration testing of some components, then we probably need to verify that as a whole. Plus integration and end-to-end testing, this allows to perform reliability testing. Continuously collect the performance monitoring, performance metrics. So this is something that might be required. So now let's look at some model project. We will be discussing it as an example for our test-driven approach. It is just absolutely hypothetical model, so we just need to have something to illustrate not to discuss something absolutely some abstract techniques. We will just go through some examples. Details are not that important. I will be introducing them step by step. But generally, what we need to develop, we have a switch. This switch is just on-off switch. It is connected using general purpose input-output line to our board with microcontroller. There is an application logic that needs to read the state of the switch and then use the transport subsystem and forward it to some HMI that is supposed to kind of be developed in parallel somewhere. The protocol of communication is well defined. We just need to implement this. And we can see, so we have like the three primary components. The one is the transport stack. We have this peripheral controls that are using this, that communicate with that check the state of the switch, and also our application logic. And I put this checklist here just to follow. So I will start with the transport communication stack, transport stack, and we will go through other components as well. So we need to start developing this transport thing. How it is often happening is that yes, we can, of course, declare some interface, then implement basically the whole stack, and only then try to, so quite simple one, so we will just, it only needs the data that it's supposed to be sent, and then, and handle some errors. We can implement it and then make an executable, deploy it on target and try to run it. Unfortunately, this is quite often happening like this. This is necessary test, but if it is initial test, so then there are some problems. So for example, of course, it can be executed only on target. So the target should be available for this. It also requires test setup. That means that if we are sending data somewhere, so someone needs to receive this data. Yeah, so we need this. And also, as this is already viable logic, so we had to implement some code there. Defect analysis will be complex because a lot of functionality is involved. If something not working, we already need to analyze quite a lot of code. Also, we saw this error here. If we need to check how our system will behave in case of error condition, we need somehow to inject it. And this might be something sporadic on the target that happens once in 100 of hours of execution. That means that if we detect it during the long run, then we fix it, then we need to retest it. So the idea is that it is just something that not very efficient. So to summarize the issues, targets should be available, might be hardware is not yet available, or there is no, I don't know, it should be startup code, everything should be already in place to really run the execution. So a test should really contain some viable functionality, so it needs to be able to run on target. And the test is dependent on the hardware software as it is. On target test, we have some conditions errors that cannot be just intentionally provided. Test cannot track any intermediate states. We have only input, and then we need to check the output, in our case, somewhere on the wires. And test results, they can be just ambiguous because a lot of functionality involved, plus platform is also involved. Maybe it's, yeah. And just to minimize those risks, and to just maximize the quality, it will be beneficial to just do some off-target verification before we try to deploy something and test it on target. What can be? So we can verify definitely the logic. We can also verify that when we are accessing some platform APIs, we are conformant to the contract. And of course, on host development, if we can run the tests on host, this is efficient. This is efficient work for and quite nice work for software engineer without necessity to deploy all the time. And of course, this on host development can be driven by unit testing. And the unit testing, this is the type of testing where the units independently verified for compliance with the contract, yeah, and they can be the primary driver of the code development. So generally, to check those units, we have some input and observation points that we can use. So we can observe, of course, and assert the direct output, like what functions are returning, what getters return from us, returning what state, what observable state the, for example, objects have. And we provide indirect input, of course, as well as function arguments or some setters. But we also have, so the classes, they can also have some indirect input and output. So communication with some entities that can be even hidden, like, for example, communication with the platform. So to test those, we need to introduce mock objects that will be substituting those dependencies. And so just mock objects are like a test double objects that have some predefined behavior and verify the access. So the interaction with them. So this will give us this isolation from dependencies. We then can easily localize the error because we are testing the separate unit. We can verify the logic for events that are infrequent or just really sporadic. We quickly get the feedback. And then we can make an independent progress of different components because we can develop them in independent environment. Yeah, so. But to enable this, we need to consider some principles of design for testability. So generally, those principles, they are, of course, are part of the best design practices. And testability in general, it is very well connected with reusability and portability because we are developing our units in the test environment to be then ported and reused in production environment. So if we apply in test-driven development. So it means that we need to design in that way that we can reuse them then in production. Yeah? So, and if we are using mock testing, then we fundamentally need decoupling and dependency injection. So the unit is just dependent on abstraction, and real or mock implementation is injected. So as composition prevents this injection, we need to think about decomposition. And of course, if we have smaller units with smaller responsibility, then it's easier to test and understand what it's supposed to do. So separation of concerns is always good. So now let's go again back to our example. So in our transport stack, we can do the following decomposition, yeah? So it really doesn't matter that much, but so we have message encoding, so we need to prepare a message that we send. We have protocol-specific timestamp evaluation. We have some logic to get the timestamp that we inject or that we place into the message. We also need to access the link layer. We also need to verify, and we also have some logic that orchestrates this whole thing together that controls the transmission. I will extend our checklist here. So, plus, another thing about decomposition, yeah? So even if we can have direct and indirect, if we can provide direct and indirect input, if we have our unit that has a lot of internal kind of logic, to test it, we need to provide a very complex synthesized input. Yeah? Basically, if we have some functional blocks, we need to provide input for any of these blocks and in various configurations, because then some blocks will be retested all the time. So we really have like huge tests. Plus, of course, some of these blocks, they can be dependent on platform. So to solve this issue, so we, as we discussed before, yeah, so we make this logic dependent on the abstractions, and for testing we provide the mocks, and for production we inject independently verified the production dependencies, yeah, so production implementations. And to do this decomposition, we can use some hints, yeah, so we can ask some questions like, what is the primary responsibility of the unit? Are there any hardware platform interactions? Is there any data transformation involved? Data transformation is always nice to test because typically it doesn't have any dependency on the platform. It can be, are there any reproducible internal operations, like for example, random number generation? Because if it contributes then to output, we do not know, we cannot then predict what is the expected output. Yeah? So we need to extract this somehow and inject. Are there any timeouts involved? It's clear, because if the code has any explicit timeouts, then we will have issues with, executing those tests with the units. Can be long timeouts, execution be very long. And this is a recurring pattern. So we are switching from composition to aggregation, basically from ownership to sharing, and we can iteratively apply this if needed, so doing further decomposition. So kind of from complex to simpler. Now about the first part that we need to implement of our transport stack, we have our message encoding. Yeah, so that this is just the example of data transformation. So we have some data that is supposed to be placed in the buffer with some header. Again, completely made up just for example. So it has some fixed values in the header. What is important, there are 4 bytes timestamp that is supposed to be provided in network order, then there is a payload size and some payload should be attached. For code examples, I will be using C++20. I'm aware that it's not available for any embedded project, but it can be downgraded to the earlier standards. I'm using also non-std expected as a third-party library and encouraged to use those structures. And also unit tests are in Google Test, Google Mock. So we can start implementing code. So to do this, to implement this message encoding, first function that we probably need is the one that will be calculating the message size based on the data size that is provided. For us to know what buffer we need to allocate to place the message later. So we'll be just returning either either size or some error if it cannot do this. And we start, so here we basically start implementation already. It's online here. We at least like specify the interface, and then we can start implementing the test cases. So here this test case just verifies error case where the data size is too large, cannot fit into the payload. And we specify here explicitly the values, and we do not reuse these values along the implementation and testing. So we do not, we follow the documentation, and actually this precedes implementation. It's important not to share, because otherwise we can copy the erroneous data. And in this case, we can simply just assert that the error is returned. So this is like the test for the negative case. We will have more of those tests for different potential results. The second function will be our assemble message function that will be already preparing the message. Yeah? So this one will receive just mutable span as the kind of as a location of the buffer. Then it will have immutable span that will have the data. By the way, spans are also, there are also backports of this C++20 feature for embedded development. This is a very useful one, especially when there's need to work with this abstracts like buffers and data, so definitely useful. And also our timestamp that we will look a little bit later, so but we need to place this timestamp. And we also implement some tests. Here it's a positive case where we have the buffer that is of enough size, and we need to make sure that it will place it. So what we are doing here, yes, we again specify the test values and buffer. And here we apply the function, and we would like to compare the prepared message with some value. But we see that our function returns optional error, basically, so expected with void. So, and we see that it would be convenient, it would be just returning span where it is within the buffer. So we verify that our interface is missing something, yeah? So that's why we can amend it. And we see that even before implementing and before kind of providing these facilities to someone, for example, or commit, we also verify our design decisions, yeah? So trying to use our code even before we implement it. So yeah, we now have this result, and we can compare our message, prepared message with the value. So here, the values are explicitly specified. I'm against, so they can be extracted into variable with the name, but what is important is that they can be kind of readable. They are not taken from the file, they are not anyhow produced. It's important for test simplicity, yeah? So we need to keep the test simple. We just have test input, output, and expected output. We should be able to compare it and visually see where the problem is. And plus, the explicit data, it documents the use case better. So if it is required, sometimes so that there is basically some processing within the test code that prepares some expected output from the test input. Most likely it's an indication that some further decomposition is needed. Then test is quite, then object most likely is quite complex. So yeah, this can be used. So here we are specifying data explicitly, and we also have here, this part is our timestamp that is in network order. So with the decomposition, we do not go into extreme. This is done by some, within the implementation of our function. It is done by utility function that is called like host to network, that has a simple implementation, but I would recommend to test it separately, also develop it using the test-driven development approach, then basically again compare it for different test cases, and then to reuse it within the more complex code to avoid potential issues. Yeah, so because it does not affect the readability of the result, but at the same time, if we test it separately, we are unlikely to bring some issues with this function. Yeah, so just from more simple to more complex structures. And we will develop more of the cases until the moment when we will have sufficient coverage. So here our implementation has, here it has full coverage. all the executed lines are green and all the branches were taken. So that means that we had our scenarios kind of triggered the different parts of the code. Yeah, so this is kind of a metric that can be used to evaluate sufficiency of the testing. Yeah, so okay, so we are done with message encoding. So after we have this test, we can implement and we have verified test. Now we have another part of our code that is called message timestamp. We need to evaluate message timestamp again. Based on real life, but made up. So we have the time source that is provided by platform that is basically something that is synchronized from some master time source. In our case, it can be HMI. This one should be included if it is available. If it is not, and the system is configured to use some fallback, we take the local clock. So basically very simple condition. So either main clock is available or we use the again. Yeah, so to make it simpler, yeah, so we have get timestamp function that has a flag parameter if we fall back to local time. And we have, in our case, we have platform API that implements these time sources. And yeah, so highlighted here. So our function and yeah, our time sources. This logic to evaluate this timestamp is a part of the communication stack. So it can use these time sources, but it is not must that it is using it. The logic itself is portable. So if we are porting the stack, and it can be ported to host or to test doubles that are supposed to be used in integration testing. So we will be considering it from the portability point of view. And yes, we need, for testing purposes, we anyway need to decouple them and somehow test to inject the dependencies on these time sources. And now we are coming to the point how we can do this. And one of also typical approaches is let's introduce abstraction layer. The abstraction layer quite often is done using just runtime polymorphism. We introduce an interface. This interface is just injected into our function. We can then test it, because of course we can make a mock object based on this interface, just inheriting it. And then an interesting part is happening. Here we are implementing the code that is using the platform, platform functions. Generally speaking, here it's trivial, but it can be something like this. So we have some function where we are passing some parameters. We also need to return value. This value must be, in some cases, should be converted also into something, into some more high-level type. And for complex logic, it can have issues, but even for non-complex, so for example, this here is an example that is done based on some real-life problem as well. So some form of the socket factory, and we have here some fortified interface with strong types. So those are scoped enums that are mutually not compatible. But the problem is that to inject this to the low-level code, we need to convert it into plain types. As a result, here it's correct, but we can just misposition them. And the interesting thing is that if we have this abstraction that is supposed to be executed on platform, the code that is dependent on the interface can be very well tested. But then we deploy this on the platform and we get the issue here because something is not working. So that means that this code that is supposed to use as abstractions is supposed to be verified as well. Otherwise, we are not. Otherwise, we introduce the risks, yes. And also about the runtime polymorphism. I mean, it's used. It's not prohibited even by the industrial standards. So the runtime polymorphism can be used. The question is that it has advantages. We can really separate compilation units. We can place our implementation can be then stay in CPP files, so we can really seal the dependencies there. This is good. And it's also suitable for runtime injection when we have some plugin architecture. That is not very typical for embedded, by the way, anyway. So, but might be. But of course, it requires the hierarchy, it requires the reimplementation of the class, so we cannot just plug in, we need to write what we just saw. And we have dynamic dispatch that can have just runtime consequences. Depending on the compiler and depending on structure of the program, sometimes can be really very well optimized, sometimes not. So those are the kind of downsides. Okay. We want to have it portable. It is a requirement. We need to consider, we need to have components that are dependent on the API really extracted, but we also, as soon as our decomposition reaches the point where we are using this platform API, we need to be able to verify access to this API. And one of the options that is also well known in embedded, this is so-called link time substitution. Yeah, so it's basically based on the idea that we are just substituting the implementation by test implementation of the framework that we are dependent on. So for our time, it would look like this. So we are using the header, the platform header. So based on the types that are declared there, we just define our mock. We provide functions that can be used to register this mock. And then we use some mock as a singleton that we can register and unregister using the functions that we mentioned. And then our test implementations of our platform functions, they will be just forwarding the calls to the mock object. This can be then combined with the gtest functionality. So in fixture on the setup and tear down, the mock can be registered and deregistered. That also will be owned by this fixture. And then we can just set up the expectations and run the dependent code and verify what is happening. The problems here is, so yeah, let's look first of all at the advantages. Yeah, so it really can be used with C code. So for testing C code, dependent on C code. Also, it is well suitable for C API. So as soon as the implementation is, so kind of declaration definitions are separated, yeah, so it works well. It does not require dependency injection-based design. So it is kind of advantage and disadvantage, but the idea is that it works well with legacy. So if we have some not very well structured legacy code, we can then cover it with tests using this approach to make it, for example, test-friendly before we are doing refactoring. Yeah, so something like that. And it doesn't introduce any overhead. So the code remains in the same state as it was. So if, for example, tooling that is used for embedded project or some specific requirements regarding optimization do not really help in using other versions. So this one is the most safe from that point of view. So, but it requires test environment that theoretically can be generated from headers, and it also, we do not prototype any decoupling there. Yeah, so the code remains as it is. So it's, as we said, it's part of the advantage, and also disadvantages. We need to have the portable, kind of the decoupled design. Plus, we also saw that there is a singleton, so that means that theoretically, if we want to somehow like run the test in parallel or something like this, we have issues. Yeah, so we cannot, because we have the mock stays as a singleton. Yeah. Our timestamp provider is supposed to be portable according to our requirements, that legend that we set. And so we need to consider other dependency injection techniques. Function pointers, another one, so quite a legacy one. Yeah? So this is also well known and widely used in embedded. This is the way how the C code is typically configured to run on the platform. This is generally looks like that. So this is the C structures. It can be slightly modernized in C++, providing like left to right member declaration using this nice at pointer T alias. Yeah. So the sample code then that uses this will just invoke indirectly. C++20 designated initializers, very nice, really. So that was in C++, in C since a while, yeah, now available in C++. So, but the idea is that we just need to assign this, some function pointers to those pointers that we inject, and then we can just inject them into the function, either as an aggregate as a time sources, or we can just inject the individual pointer if we need. So. It can be used with standalone functions, static member functions, and captureless lambdas because they can be converted into to the pointers. So the limitations are clearly, so these, when we're using the function pointers, we explicitly make the call, bring the indirection into the code. It can be, again, by the compiler eliminated, but it is there. So it depends how good compiler it is and what are the settings. For example, if the compiler, if the build is for, so if the optimization for space is specified, and this is quite often the case for embedded, then, for example, GCC, it's not already aggressively inlining, and if it does not inline some functions, then it's also quite often stops also removing the indirection within these functions. So as a result, we are losing runtime efficiency for the generated code. Yes, so something like this. And function pointer is also not associated with any object if it's not specifically designed for this, but if we're talking about when we try to adopt already existing API, it's most likely the case. So if it doesn't have any context, that means we are again using some singleton mock to substitute for test purposes. So again, similar to link type substitution, but we are injecting on runtime. Alternative to injection of the function pointers is just to inject and make our code dependent on polymorphic functions wrapper. So theoretically, what we can do, yeah, so we can use standard facility like a CD function for embedded. Embedded is different. Somewhere we can use it. Somewhere we need to use some non-allocating alternatives that have the static block for capture list. Because they cannot, because sometimes it's just not possible to use dynamic memory allocation. The CD function needs this according to standard. So our code will be dependent then. I will just switch now to some class to hold these dependencies. Yeah, so from function to class, we will all have timestamp provider, and it will be dependent on this function. And then this can be used like with very different types. Yeah, so we can then inject just some lambdas, so closures that are the result of the lambda's expression. We can standalone functions, we can capture some object, and this is really convenient. Yeah, so because we can simply connect some different pieces of code together without necessity of rewriting the kind of introducing the more of the code. Yeah, so the boilerplate code can be kept quite minimalist. So we can, for mock testing, we can either forward the calls to the mock, or we can inject some mock objects that have co-operator by reference. Yeah, there. So that's all things are working, and the code then that uses this will look like this. So just calls. So the function itself is callable. So the wrapper itself is callable. But the problem is that it's really like can introduce massive runtime overhead, and this runtime overhead, some Clang namely, yeah, so it's really good at optimizing this code, if it is static one, yeah, so if on compile time it's known what is injected into this object, but this is quite a unique feature that it has. GCC cannot do this, yeah, so for example, so far, and one wrapper object per interface method, so we need somehow like to inject many. So what are the alternatives? I mean, we need to consider, yeah, so we have the quite a static structure of our code because we are in embedded. We do not quite often need those runtime features. So we can try to focus more like on the compile time options. And we can try to use compile time polymorphism, yeah, so for these cases. And here it's quite simple, yeah, so we have dependent code that has to be generic. The dependencies type is specified as a template argument. And what is needed, that the dependency and dependent code, they are supposed to be compatible. Yeah, so that the substitution, the template substitution is supposed to be successful, yes, or should not fail. In our case, so we can invent something like this. So here it's a bit, may look a bit complex. So the idea is that we have template, timestamp provider becomes a template. We use the forwarding constructor, like with perfect forwarding, so that is also a template, and we link. So the types of so we use std forward to forward the arguments to our members. Yeah. So based on the type that was deduced from sync and local template parameters, and then we can also use the deduction guides just to link those constructor parameters into template parameters. So what we can achieve, generally speaking, is that the get sync time will be dependent on the kind of value type of the object that are passing the parameters. So, and then we can have the same cases that we had with the type erasure, but in the compile time. I mean, it looks like that, but of course it's not, because those are all different types, yes? So because they are instantiated with some specific types. Here, the example is that we don't need to use std ref before because we have a deduction of L value of our parameters as L value reference. Yeah, so we can do this, and this will we will avoid this runtime overhead. Yeah, so we can have the code still testable. We can inject the mocks, but we do not. But we can avoid the runtime overhead for the code pieces where we can have this. The code that uses it will be exactly the same in terms of kind of invocation, and we can then use it also with standalone or with our C++ functions. But there is one detail here. So if we are here, we have inline function that just modifies just kind of a wrapper that needs just rescales a bit the unit that is used in the function. And we also get sync time is still our platform function. If we inject them like this here, like what we are doing here, yeah, so we are just providing them and injecting them this way. Their types will be deduced as references to functions. Yeah, so and generally they will be injected as pointers to functions. That means that we will here introduce again indirection. This would and if with the same consequences, kind of inhibited optimization of the compiler. If we do something like this, we do not introduce any indirect calls. So here the calls are wrapped by the lambda function, and we do not have function pointers here. So we, generally speaking, do not introduce it, and it will not magically appear somehow there. So typically, yeah, I mean, with the good compilers, yeah. So the thing is that if we just calling like this, so as an so this is one problem that we have. Another problem is that kind of injecting every separate method, like here, can be also problematic. Yeah, so a bit maybe unsustainable if we have some API with more methods. So as a kind of remedy to this, we can try to switch to the option where we just inject some form of the configuration that will have APIs that we require. In our case, those are this get sync time, get local time. And again, we can use, for convenience mostly, our perfect forwarding constructor and our deduction guide to make config either a value or the reference and make the code compatible with other L value and R value. So this is primarily for convenience, because then we can have where we do not need to inject dependencies, we can make them just to be copied there, so not to have them externally. And for testability, but what is really important is that we can pass here a reference. Yes, so if, for example, we do not want to build this kind of constructs, we can. What important is that we can pass here a reference. And then the interface will look like, so our class, our configuration will look like this, where we are just calling the functions. But we again, so we avoiding indirect calls, but we are again coming to this point where we had with the runtime polymorphism. We are again having this code that does something. If we need to pass and forward parameters here, we can have troubles. Yeah, so just accidentally. So the solution theoretically to that can be just to use some perfect forwarding of the function arguments and the return type. So here we are in the dependency. We're doing this. So we just we define some function that will be just forwarding everything there and back. Yeah. So into some function and then forwarding the return type. Decal type auto to support also the C++ functions that return the references. And this can be also generalized using macro. I think that for this particular purpose, it can be quite convenient. Yeah, so the idea there then that we can simply do something like this, where we specify, yeah, we want to have the forward call. I'm bad at naming, sorry. Maybe some better naming is possible to do. So we can use, like with get sync time, get local time, we can also use our get scale time. And this will not, again, we are not using pointers here. So again, going back to this, yes, so if we are, so our configuration that we are injecting, it can be also complex. That means that if we have something complex there, we again need to consider testability of this particular piece of code. Yeah, so we can inject something, we can extract something that provides some API to our to our logic, but this logic might still be complex. We need to use decomposition and testing it as well. So this is, and having smaller, clear pieces. So this implementation will still be working, by the way, with the pointers. If we would like to, we can inject them because it's compatible. We also can even inject our interface by reference. One more detail. This logic is still dependent on the platform contract. Because according to our platform, so this get sync time, it should be more than 0. So 0 is invalid value. So, and we also use timestamp t. This is our platform type. To remove this dependency, we need to move this into configuration as well. Yeah, so if we can move it here, like is valid timestamp, this check, and default timestamp, just a function that will be returning the default value. Plus, we need to inject the timestamp type. This will become a part of our configuration, and then it will, our configuration for our platform can look like this. So, yeah. And there is also interesting C++20 feature that we then can constrain the constrain the required type, the required configuration type, using just using a concept. So we can specify that our configuration needs to have functions that are returning timestamp. So we are not very strict here. We just specify the relations between the return and the types, between the types that are returned and the types that are accepted by some of the functions. Plus, it needs to have those type aliases there. And then our configuration, if we implement some, can also be, without even an instantiation, can be verified for compatibility. Yeah? So using just this concept without instantiation. Yeah? For testing, we can have a mock object that will be injected, and the test will look quite simple. Yeah? So just our mock object is supposed to have some expectations and verify that the calls were done to it. So our logic will be verified. Okay, so this was actually the largest part of the talk because we looked through the different dependency injection techniques, and we'll use those a bit. Yeah. So compile time polymorphism. Yeah. So that's what we discussed. We have we can avoid indirect calls. We keep the good potential for optimization. the code stays, yeah, so still available for further compiler optimizations, and we can substitute dependencies on concrete types. So, but yes, it comes with the cost that dependent code has to be generic. Of course, it's static dependency injection, everything happening on the compile time, and the dependency and dependent code errors need to stay in a single compilation unit. Yeah, so unfortunately, so this can increase compilation time. It also can be problematic in some cases. Yeah, so but the advantage here is that it gives us really good options for testing code that is not that easily substitutable, yeah, so especially with the concrete types. So for example, here there's just another example. So we have some function that is supposed to write something into object that is like output file stream. We need to verify that it was opened correctly, that it was checked, that there was some write attempt. So we can make a abbreviated template, yes, based on the concept that somehow requires the interface of output file stream. And the implementation will be just triggering this, so just using this object. We can then, the kind of backward compatible version will just really need to have to be dependent on the template parameter. And here what we can do, we can have we can make a mock object, yes, so, and that we can just inject instead of our stream. So for production, we are injecting the real off-stream object. For testing, we are injecting the mock. And we can verify that it was opened with the file name that was provided, that there was check, and there were some insertion into stream triggered. Same thing, by the way, typical problem, yeah, so code that is supposed to be implemented, that is supposed to be executed in a concurrent environment, yeah, so we have some synchronized stack that can be done as an adapter for a container, yeah, like something, and with some default template parameters, yeah, so we have here like vector and std mutex, but for testing purposes, we can specify other types. Yeah, so again, with our technique with the forwarding constructor to, again, for convenience, yeah, so because it can either own it or we can inject them. And then so the template is based on the concepts, yeah, so those concepts, it's either this lockable that follows the lockable named requirement, yeah, and something that's stack-like accessible that requires that there are functions available that are needed to implement the stack in the container. Yeah, so went a bit ahead. Yeah, so the functions are just constraining and requiring the functions that we will need to implement the stack efficiently, yes. And then we can verify the code. For example, here, yes, we need to lock the mutex before we appending the value to the container. So that means that if we do the mocks and inject them, we can verify that in sequence the calls are correct. Yes, so we need to lock, then push back, then unlock. So here is the injection, yes, of the mocks instead of the types, and instead of the kind of real production types. And here is the verification. And for example, we can detect the problem is we forget to name this variable and create a temporary that will not overlive this line, so and that will keep our container unprotected. This will be detected because the lock and unlock will happen before the pushback. So we can verify this, and we can use some other container types, like for example here just default constructor types like default. So to make it possible just to create the stack with the default template parameters. Yes, so here we can just have it like this with integer, and here we can use this adapter really in the way that we inject the already existing objects. Okay, so now a short summary about the dependency injection. Yeah, so we know that the behavior of tooling differs, and we really need to consider what is available for us, what our tooling is capable of. we know that optimization for space that is used for embedded projects quite often can reduce inlining with some other consequences, like also that indirection can stay in the code. Compile time solutions, they unlikely to really block the compile optimization effort, basically. Why I'm saying unlikely, because yeah, there are different compilers, quite many of them. It's really hard to say how it is with to give any guarantees. And really, if we have some hot path in our project, in our software where we need to really have efficiency, this kind of injection, and we need still to verify this logic, we can use the compile time injection for this. Yeah, so yeah. So now next, it will be faster now. Yes, so we have also our link layer interface. So this is something that connects to the HMI, and access to this link layer is controlled by a function, but by the platform API. Here we have, it returns to us some structure that gives a descriptor of the buffers that can be used to fill the data that can then be sent. We also have functions to allocate frame. We also have functions to commit or release frames, depending on what we want to do. So this is just the platform API, and we see that, so this will be a core component. We want to have it tested, and also we would like to provide some more high-level and safe API for this. We see that there's a clear acquire-release semantics. We would like to have the RAI wrapper for that. So if we apply the test-driven development approach, yeah, so we need to find the way how we test it. We discussed already, we can, theoretically, the low-level code unlikely to really be portable, yeah, because here we have so it still can be portable. There can be portability between the family of different platforms, but typically it's not. It shouldn't be overestimated, yeah. So it's not that the same code that's used for one platform will exactly fit into another problem because of different API. But on the other hand, we can. So that means that we can try to use link time substitution, or we need to we can use compile time injection, because we definitely do not want to, if we don't want to introduce the overhead, but at the same time, maybe we just would like still to decouple the access to the platform from the kind of class, from the wrapper itself. Yeah, so. Anyway, so if we are using the link, the compile time substitution, so what we can do, we can have just our link layer implementation that will have acquire frame method, and will return the frame, the frame descriptor that will control the acquired frame, and we inject the configuration the same way as we discussed before. And here we just can specify that those frame that was returned in the test implementation from the platform is supposed to be properly forwarded into the wrapper object. Yeah, so we just check that those parameters really fit, because we do not access the low-level values that were returned, but we already used the high-level API to do this. And we just make sure that they are actually correct. And we also check that release frame was called, because we do not do with this frame anything. And if we would like to make the check that we are committing this frame, basically returning it to the layer, we need to make sure that the commit frame was executed. Yes, so this is something like this. The idea is that we definitely need to check that the parameters go in there and back correctly. So the implementation of this acquire frame, it needs this. So it uses this allocate message that is supposed to be injected as a part of the configuration to make it completely dependent if it is needed. Yeah, so we also need to inject the type, and we need to take out the checks for errors into separate functions. Anyway, so following this approach, we can have a coverage for the function that really uses the platform API. So here what is happening, so this allocate message, this is the parameters will be forwarded to the platform API. We make sure that they are that the contract is somehow fulfilled and we provide the correct parameters. Okay, so now link layer is done. Then again, we still have this transport logic, our primary logic of our transport component. Here we switch from the send message function to the class because it has several dependencies. It will be just easier to manage this. We can have some concepts that will specify the interfaces that are needed. And we can again apply the test-driven development approach before we implement this logic. We have our test data, we have our mocks for all the components, and then so injecting those dependencies, we can run the code, we can execute the code where we're just checking that the orchestration logic is correct. Yeah, so we check that the that the message size that was calculated by the calculate message function is correctly forwarded to a query frame, for example. Yeah, so we are making sure that just the data is correctly dispatched in between of the function calls. Here, that the frame is associated with a proper buffer that is then forwarded into the assemble message, that this buffer is used, and other dependencies like timestamp is correctly provided. Yeah, that commit frame is called. We can also have some check the resilience of the errors because we can just trigger the error conditions here. So it should once return error from link layer, but it should retry and then everything will be fine. So we can imagine the complexity of this code if we of this test, if we will not extract this message building or timestamp evaluation, all this logic will be here as well. Yeah, so we will need to provide much more complex cases. By the way, this expect calls, we have 3 dependencies. It also can be some indication. Maybe we can kind of rearrange it a bit. Yeah, so use some aggregation to have slightly different layout and maybe reduce number of dependencies for this particular class and just kind of rearrange them a bit. So, but we here can only, the advantage is we verify only the logic of this unit without necessity to verify other components. So logic that we move to other components. Okay, so, yeah, so our transport stack is done. Now, it's quite a short part. So, one remark, important remark. Yes, so what is good with compile time injection? Yes, so it enables top-down approach. So we can start implementing the logic of the module without dependencies and then implement the dependencies. Now we can use the concepts to constrain the interface that can they can implement some form of the dependency inversion. Can look like dependency inversion maybe, yeah. So because we can specify that the concept is supposed to be then fulfilled by other units. On the other side, it also can be done bottom up when we already have the existing pieces, and we can assemble them into logic just by providing a templatized code that will be handling them. And we can then achieve some decomposition without runtime overhead. Now, TDD of hardware-dependent code. Let's shortly look at our layout. So when we are talking about dependency on the hardware, what it is. So in embedded, typically, so we have those on the microcontroller. We have those pins, yeah. So and those pins they can be wired on the board. So yeah, my advanced illustration skills. So we can use one line to connect it to one of these lines can be just connected to some peripheral. So those lines can be connected to peripheral devices. In our case, one of those lines is connected with the switch, and the state of the switch is basically propagated by the state of this line, percent of the current on this line. So those lines are called general purpose input-output, and they are controlled using so-called memory mapped input-output. So the idea is that at the state of particular lines, it's a bit more complex, but generally, yeah. So the state of these lines is reflected into the bits into some memory allocation. And this memory allocation is architecture specific, so it's just known. In this case, it's just address 42, where this byte that sometimes is called register, or for it's not the CPU or a microcontroller register, just called like that. And so for us, the switch is located in the byte number 4, yes? So we need to control it. How we can do this? The strategy to test the hardware-dependent code can be the following, yes? So we can develop or use existing, there are several, verified abstractions that encapsulate MMIO operations. We then can generate layout using abstractions. So the layout, kind of translate the layout from the architectural documents or SDK headers into the layout based on those abstractions. And then we use compile time dependency injection to have the logic verified that uses those abstractions, yeah, that's supposed to use those abstractions. And to look at this as an example of this approach, so we can try to implement some very simple abstraction to access our bit that gives us the state of the switch. Here we, again, are based on the templatized code. So we need to have some form of the location-like object that has the static function pointer that will be returning the pointer to this register, yes, to this block in the memory where the data is supposed to be read. We can constrain that it's supposed to be unsigned integral type. Then this one can be used in our abstraction. So first of all, we can verify that the offset that we provide of this bit is within the bound. And this abstraction, location-like, will be providing to us the pointer to this object, and then we are doing this access, just checking the state of the bit using the mask. This is a simple abstraction that can be implemented. The idea is that for the testing purposes, we can have the kind of mock location that will be just returning the address of some object of integral type. Here, so we can, according to C++ standard, we can take the address of the static object as a non-time template parameter. And here we can just verify that our code is correct, that we are accessing the bit correctly, so one of the test cases. For production, we can use another location that will be just giving us the address, that we specify address in the form of literal. And it will be reinterpreting this as a pointer to as a pointer to the type that corresponds to this register in the memory, having the same size, and then we can access it. So we can use the alias that will be using this abstraction, and this alias will represent something meaningful for us. In our case, this is our switch GPIO line. The simple polling driver then will be just dependent on the abstraction of our bit. It has isSet function that returns bool. Trivial logic in our case is that the bit that is injected is just, its state is returned from the press function. So we're just taking it when we ask the driver. Of course, for more complex structures, there will be much more MMIO operations involved or more complex logic. But it can be then also just verified based on the bit mock. And for interrupt-driven driver, yes, so we can use different approaches, yes, but we can also introduce a driver that will have some client-specific event handler and with some specific signature, and that we will store as well. And we will need to have ESR function that will be triggered from the interrupt service routine. So depending on the architecture, how it is done, so most likely the driver will be the global object, and this will be triggered from interrupt service routine function. And again, in our case, the logic is trivial, just the state is propagated. We can then trigger this function to verify the logic that is typically will be then triggered by the interrupt service routines. Okay, so we now also implemented the peripheral controls. And so a couple of words about the unit testing and decomposition. Yeah, so what we saw, so what we were doing, yeah, so we were from requirements of some components, we had to do some decomposition to make the code a bit more testable. Actually, testable. Then we were switching to design of this component, iteratively doing the decomposition if needed. Then from the design of the component, we were trying to implement the tests and run those tests, maybe. But also we writing the tests, we were getting feedback about the design of our components. Yeah, for example. Then we were implementing component and iteratively again implementing some tests. From each of this position, we could then go back down to requirements potentially, yeah. So because we could see that something is not compatible for us, yeah. So the process of TDD with unit testing in a more complex perspective looks like this. And in some cases, it is also possible that some issue for the backlog can be issued because we've seen that some asset can be implemented that is reused in different components. Okay, so as a result of the project of this process application, yeah. So what did we achieve? Yeah, so we could verify the usability, yeah, of the proposed interfaces. We could clarify the requirements for some components. Yeah, so we see that all the dependencies are in place, that it can work based on the architecture that is offered. We could also elaborate requirements for the dependencies depending on what approach we were using. We also verified the implementations and we supplemented them with tests. Then tests can become a part of CI. Yeah, so, and tests, they document the usage because we had a lot of examples how we could use our components. And we could then do the further development following the same TDD approach, of course. So we should do that. And those verified code, having the CI process in place, we keep the verified code change-friendly. Yeah, so we can do that further. Now, one remark. Yeah, so, but is it possible to develop the whole system based only on unit testing? Yes, so is it sufficient? Actually not, because there can be incorrect assumptions and understanding of specifications. Yes, so we might be misunderstood something. Also defects in the tests, defects in test implementations, just in the tests or in mock objects. Plus, there can be, especially for cross-platform development, there can be some portability issues. And we are developing the solution that is supposed to be deployed on some specific target. So that means it should be tested with this target. Because the platform can have issues as well, yeah? So we need to be sure that everything works. So that's why we are just kind of coming back to our iterative structure where we still have integration and end-to-end testing, yeah? So that are supposed to be considered as well, and that's why we said that we need to plan those activities accordingly. But one more thing, yeah, so if unit testing can have flaws, yeah, so is it needed? And of course, we discussed advantages before, yeah, but I would like to emphasize, yeah. So again, first of all, yeah, test diversity really increases confidence. And those issues, they generally do not invalidate the advantages, yeah. So we still have short execution time, we have error localization, we have our tests that are portable. And yes, we are driving the code development by unit testing, while those more complex tests, they can be available at much later phases of development because they are hard to implement, can be hard to implement. Mostly, yeah, there are some standard solutions for non-embedded. For embedded, this is quite hard, quite often hard. Now, generally speaking, assembling all those things together, our last piece of code. So first of all, we have the struct message builder. We never implemented any class message builder. We just make this, so we just inject these two standalone functions now as the methods. So basically kind of attaching them to some class. Those are the functions that we developed in the beginning. Yeah, so as a part of the message handler class, we have this error T that is required by the concept. And so kind of our main will look like this. So the pieces that are used that could be hidden, they are now kind of exposed. We need to configure them all and basically assemble some logic. And there is also this application switch monitor that is kind of part of application logic that is basically trivial. Yes, so we will not need to cover that. So that's basically all. And yes, so we put the check on our application logic. And then I think we will finish with this talk, actually. Yo. Please, questions, yeah?
So, in other...
Yeah, well.
There is many other languages where actually mocking mechanisms are more simpler than in C++, and usually there is a lot of developers that go into the traps of over-mocking, and mocking so much that at some point actually they test more than mock than their own code. So what is actually your advice, or when do you think that the split is necessary, or what is your metrics to find out that, okay, I need to mock these components and I cannot, I mean, except for example, if it's a component that you cannot have access at all, like a database or whatever, but sometimes even just inside of your own application, multiple components you want to mock because it's just too much to test. So.
Yeah, so for me, the metric is that the test, when we provide the expected, I think as you're using microphone, yeah, let me repeat the question just in case. Yeah, so the question is that what is the measure, how we can how we can understand that is basically enough and decomposition has reached a state where there should not be more of it. Yeah, so when it's like the code is already splitted well and tested and can be tested using mocking. So for me, the criteria is that the tests, they should be easy to understand, basically. So visually, there's already, from the test, there should be immediately visible, kind of not immediately, but at least when you see the report that something is failing, you can really, by your eyes, compare what is wrong there. If you see that, okay, there is an expected value and this expected value does not fit, then probably you reach the decomposition level where the operations are already on that simple, that you can easily just check the output of the unit test and find the problem. So if you can explicitly specify the expected results, this is something that I would really like to achieve, and this, I think, for me, is a kind of primary criteria of the nice tests and also a sufficient level of decomposition. Did I answer the question? Please? Please, yeah.
Thank you. In the beginning, you had the example with the expected, and you used the stood span as the error type. I wondered if it's safe to, because you're returning a span to some string which is allocated nowhere.
No. So everything, all the spans, they are returned to the data that was provided. So the buffer where the message is supposed to be located, it is provided as the input for the function. It needs to be of sufficient size, otherwise error will be reported, or if the message can be located into this buffer, then the span indicating the position of the message will be returned within this buffer. So it is span to the span, kind of.
Okay, I'll need to look at it again.
I will show you the slide. Yeah, that will be easier. Yeah, sorry. I think it's just let me find this somehow. Yeah. This is the timestamp. Okay. Yeah, so here, this is data. This is immutable span. And it's supposed to point into the memory that was provided within this buffer.
Yeah, what is the type of error T? I thought it was span. Oh, it's
error T is just error code.
Okay, so
initially it was just a kind of optional error. Yes. So and now we amended it to have span for quicker. So we can evaluate, understand where it is if we are using another function like this length, but it's just convenient if it is provided as an output. Yeah, so we can use it simply.
Thank you.
Please.
So I noticed in one of the test cases you had a large sequence of expect calls beneath each other. All of these calls were going to a mock object, and the results were being sent to the next mock object in sequence. Can you comment on the value of such a test?
Yes, because you're checking the logic that orchestrating the access to the dependencies. And you need to make sure that the data that was returned by the mock correctly forwarded to another one. It's not that simple in the way if you have, so the example code and the orchestration code is quite simple. On the other hand, that's going back to the question, how much do we extract, yeah, so into the abstractions. So of course, here it's really simple in a way that, yeah, we call one, we take this, we forward this. If we have some more complex logic there, so the value returned from one dependency can be modified before it passed into another one. So if there are some issues, we can detect this.
So the question would be, if you have that kind of logic, either you are doing some work in the function and that should be extracted, or you are not doing work in the function, in which case your test is just a copy of the function, with the function invocations modified to be an expect call.
I think we can reach this problem, and might be this example kind of goes into this direction because of the kind of illustration purpose that I did. On the other side, that I think that so we still have the issues with slightly non-trivial logic and with slightly more complex dependencies, where we still have all the things where we need to provide the inputs and outputs, and we need to process them, and there where the error can happen. Yes, so then we will have this. So here, basically everything is extracted in dependencies, and almost nothing is happening in the function itself. So that's why it looks like that.
Okay, thanks.
Thank you. Well, you're waiting for me, I need to say. Then there's no more questions, yes? So, okay, yeah, thank you very much for being here, and thank you very much for your attention. Hope that was interesting for you, yeah? So then, thank you very much.